Hi, I'm Ashton D'Alessio. Welcome to my presentation on traffic accident analysis, understanding key factors that influence traffic accidents. Let's begin. This poster details my research project on traffic accidents, starting with an abstract and introduction section, moving to data collection and methodology. From here, we move on to descriptive statistics, and finally, the results and conclusion. There was a lot to unpack, so let's take it section by section, starting with abstract. Have you ever been in a car accident? Most of us have at least been in something as small as a fender bender or a bump into the mailbox. But did you know that traffic accidents account for 2.3% of all deaths globally? Graph 1 on the right shows this, with 1.2 million deaths from traffic accidents in 2021. By analyzing a data set of traffic accidents I've collected from Kaggle, created by William Oliveira, I have identified two key factors that influence traffic accidents and created a model that best explains the output of accidents using linear regression. I have also performed a hypothesis test on whether the average amount of accidents differs from urban to rural areas. The conclusion of this linear regression analysis supported the conclusion from the urban-rural hypothesis test, but with more context, showing all significant factors. My hypothesis was that pavement quality, average speed, and traffic density would be the most influential, and urban areas would see more accidents. My research questions are, what are the factors that significantly influence accidents the most? And is there a difference in the average number of accidents between urban and rural areas? In 2022, there were roughly 4,200 deaths from motor vehicle accidents in the United States, according to IIHS.org, an independent, nonprofit scientific and educational organization. Included is an urban and rural comparison. Accidents used to happen more frequently in rural areas, but a point of inflection between 2012 and 2017 sees urban areas increasing to around 60%, while rural decreased to around 40%. Although only 20% of people on average live in rural classified areas, an average of 41% of accident deaths happen here. This average is calculated from states' percentage of urban-rural deaths. This furthered my interest in the variable urban-rural in my data set, leading it to believe it was a key factor. Shows graph 2 on the right. My initial curiosity and exploration into this data set stemmed from my interest in ski resort mountain operations data, specifically data gathered by ski patrol related to injuries and collisions. As this data was difficult to come by for free, I chose to use a traffic accident data set because the data collected is like that of on-mountain injuries: victim condition, traffic density, environmental and weather conditions, and trail and road conditions. Finding key factors that influence accidents is crucial to understanding how and why they happen. Through this understanding, we can make efficient, calculated changes to decrease the number of accidents and injuries, just like IIHS.org does through research and analyzation of traffic data. Data collection and descriptions. The dataset titled Key Factors Traffic Accidents captures factors influencing traffic accidents in both urban and rural areas. It provides detailed information about environmental infrastructure and behavioral variables that are crucial for understanding the dynamics of road safety. The dataset is entirely fictitious and has been created for educational and illustrative purposes only. It does not represent real-world data and should not be used for decision-making or policy implementation without validation against actual data sources. This dataset is composed of 12 total variables, with 2 of the variables in the dataset being a description of the variables. The variables are as listed. Accidents. Number of accidents recorded as a positive integer. Discrete. This will be my response variable for both research questions. Traffic fine amount. Traffic fine amount in thousands of US dollars. The traffic density is a factor from 0, which is the lowest, to 10, which is the highest of traffic density. Traffic lights, which is a proportion of traffic lights from 0 to 1. Pavement quality, which is a factor from 0, very poor, to 5, excellent. Urban area is a binary categorical variable, with 0 being rural and 1 being urban. The average speed is the average speed of vehicles in kilometers per hour. The rain intensity is a factor of rain intensity from 0, no rain, to 3, heavy rain. Vehicle count is the estimated number of vehicles in thousands as an integer. And the time of day in 24-hour format, 0 to 24. Note, this variable is not as described and crashed RStudio when included. I removed time of day variable before analysis. All data is quantitative except for traffic fine amount, traffic density, pavement quality, and time of day. Rated 10 out of 10 for usability via Kaggle, but time of day is not as described, so I would not consider this data set a 10 out of 10 for usability. Methodology. Before starting to answer my research questions, I explored the data set and its data types, converting non-numerical data types to numeric and checking for NA and null values. Both research questions have the variable accidents as the response variable, or the variable that we are trying to explain for. I started with my second question using a two-sided hypothesis test to see if there was any difference in the average number of accidents between rural and urban areas. I then ran a correlation test to further explore the relationship between these two variables. After running this test, I realized that my variable accidents is a discrete variable and is not continuous. This is when I realized I had to check the three conditions for linearity before moving on to my next research question. I did this by fitting a line and checking the independence of residuals and constant variability. Conditions were mostly satisfied and accidents looked to have a normal distribution, other than it being a discrete variable. I chose to proceed with linear regression due to the large size of the dataset and its consistency. The way that this model was produced is by adding and subtracting variables based on the p-value and t-values in Table 1 on the right. The lowest p-value has priority first, and then the highest difference from 0 t-value has the second. For example, traffic fine amount has the lowest t-value, but it is also equal with other variables. So we looked at the t-value, which is 222, indicating this variable has priority since it is the greatest difference from 0. It will be taken away last and added first during model selection. Descriptive statistics, null and NA. No nulls or NA values were found in any variable. Image 1 shows this on the right. The output of table is.na function shows that all inputs are false, meaning that there is no NA values. Accidents. The average number of accidents recorded for each incident is 20.63, with the median being 21. This suggests distribution is symmetric, indicating normality, because they are very close together. Same for traffic fine amount. The average fine amount in the data set is 5,448, which is extremely close to the median 5,428, suggesting distribution is also symmetric, indicating normality. Urban area. With the urban area being binomial, with 0 being rural and 1 being urban, the distribution summary has almost 70% of inputs being urban. The remaining variables all have extreme outliers, containing max values greater than 990, skewing average results. A summary table of descriptive statistics is shown in Table 2 on the right. Notice that rain intensity, average speed, traffic density, vehicle count, pavement quality, and traffic lights all have a max value greater than 900, while their third quarters are very far from that. The results produced by the two-sided hypothesis test supported my original hypothesis. Sample estimates explain that on average, rural areas will see 19.5 accidents, and urban areas will see 21.1 accidents in the thousands. The coefficients indicate urban areas are expected to see 1.6 more accidents than rural areas. Additionally, the 95% confidence interval does not include a 0 between values, indicating we are 95% sure that a 0 amount of difference is not included. This leads us to reject the null, stating there is strong statistical evidence that there is a difference in accidents between rural and urban areas. The actual effect on count variable accidents is described by the coefficient in Table 1 below. The results produced from this model gave two significant key factors, traffic fine amount and urban area, none of the factors in my original hypothesis, and explains for about 60% of the variance in accidents. The graph 3 on the right shows that for every 1,000 increase in fines, the area or time saw a 1.5 decrease in accidents, and areas classified as urban saw an increase of 1.6 accidents. Although the model produced statistically significant results, the dataset did have its limitations. With the response variable being a discrete count, general linear regression would have been a more appropriate approach, but was not covered in this course. The time of day variable would have been a useful factor, but conversion proved to be too difficult and was removed. More exploration into the relationships between key factors and other variables could explain bias, such as the possibility of high traffic fine amounts being more present or enforced in rural areas. Considering the dataset is entirely fictitious, real-world insights should not be inferred. This concludes my project.